All right, grade 10s, let's discuss populations and sustainability today. We just finished in our last lesson discussing, what did we talk about? We were talking about, it was our unit intro, and we were talking about sustainability and how an ecosystem has to be able to withstand different pressures. And then the difference of how we cycle material through ecosystems, the difference between cellular respiration and photosynthesis. So today, we'll move on to populations and sustainability. And we have only 15 slides to get through today. Let's get started. Just want to double check that I am sharing my screen properly here. My mouse is driving me crazy today. Yeah, we're good. Okay, cool. So populations and sustainability. What is a population? A population is a group of organisms of one species that live in the same place at the same time and can successfully reproduce. Because if a population can't successfully reproduce, that population is not going to be around for very long. So has to be the same species, has to live in the same place, has to live at the same time, and has to be able to successfully reproduce. Populations increase when individuals in the population reproduce at rates greater than what is needed to replace the individuals that have left or died. That makes sense, obviously. If we have more members of a population being born than we have dying off, obviously that population is going to continue to get bigger and bigger. Now, the populations don't just grow in a linear sense. They don't just grow on a graph in like a straight diagonal line. They actually grow on a curve, something called exponential growth. Exponential growth is growth that starts off really slowly and then it accelerates very, very rapidly as you move forward. When you graph population against time, this population increase and the fact that it's happening exponentially is going to create something that we call a J-shaped curve. We'll see on the next slide here what a J-shaped curve looks like right there. Not the best looking J, but you can see that we have this curve. This is an exponential curve here in which we are examining the population of elephants through the years 1900 to 68 or so. What we see here is that the elephants were reproducing at their population was increasing at a pretty slow rate until 1960, at which point it kind of took off when the elephant population became protected inside of this national park, so they didn't have poachers and stuff like that that were kind of pairing off the population at an unnatural rate. And then we experienced exponential growth inside of that population. So that's where that J shape comes from. So without any sort of limit to the population, we'll talk about what these are called later, without any sort of limit, the population will grow at an exponential rate. Now that seems like a good thing, but it's actually not, because exponential growth cannot be sustained in nature. Remember, we talked about ecosystems. We talk about ecosystems being sustainable. Well, an ecosystem has to be able to sustain the entire population and all of the nutrients that it needs. There's no ecosystem that has an infinite amount of resources. So having an exponential growth of a population doesn't make sense. You can't sustain it. So no ecosystem has an unlimited supply of everything that organisms need. And these restrictions that don't let us have that unlimited exponential growth that populations naturally want to have, these are called limiting factors. They happen naturally inside of our ecosystems all around us, which limit population growth to not be so exponential. What are limiting factors? So as a population increases in size, each individual inside of that population then is going to have access to fewer resources, which is going to limit the growth of the population. So think about, all of the fish in a pond, right? There's only so many resources for each of those fish to be able to eat. So if that population of fish increases in size exponentially, well, then all of a sudden each of those fish are going to have access to fewer resources inside of that pond. Okay, this relates directly to this right here, competition. All of those fish then are going to have to compete to get the food from the other fish. So this regulates population growth in a natural way. We have two other ways that we can regulate population growth. I'm going to post a link to a video on symbiosis. I want you to just watch it. Um, and I might get you to fill out just one question on it, just answering maybe your thoughts on the different types of symbiosis that there are. This is a relationship between two animals that is potentially beneficial for both, beneficial for at least one. And then you've got predation. Predation is a predator-prey relationship. Think like wolves and or foxes and rabbits, right? So the foxes will prey on the rabbits, uh, and the rabbits will have a predator chasing them or preying on them, and that is the fox. So that's the relationship there. Those will both control population growth, obviously. There are two categories of limiting factors. The first category is density independent factors. These are factors in an environment that don't depend on the number of members in that population per unit area. So it doesn't matter how densely populated the area is. Now, what this means is that you can have, downtown of a very busy city, or you can have rural, Manitoba, where everything's very spread out, and these factors will still affect both populations in the same way. It doesn't matter how densely populated the area is. These factors are something we call abiotic. They're non-living. So they include natural phenomena. Usually, basically, when we're thinking about density independent factors, I want you to think natural weather events. So extreme storms, droughts, floods, fires, cold snaps, and even heat waves. Okay. You can also have pollution of air, pollution of land, and pollution of water. This, as a result of human activities, can also limit populations. Now that brings us to our other kind of limiting factor, density dependent. These are the ones that it does matter. It does depend on how many members there are of a population in a certain area. These factors are biotic factors. These are things that need to can affect a densely populated area more easily. Things like disease or parasites or even predation, a predator-prey relationship. If a pack of wolves finds a very densely populated area of deer, then they're going to have more prey to be able to hunt. And then competition. It also matters, right? How densely populated an area is if we're competing. Disease is in there because diseases spread, right? When a population has high numbers, disease is transmitted easily from one individual to another, and it spreads very quickly throughout that population because contact between the individuals will occur more often, just naturally. Now, what this does, these density independent and density dependent factors, these limiting factors that don't let us have exponential growth, they actually end up forcing the population to reach something called a carrying capacity. This is the size of the population that can be supported indefinitely, so for as long as we need it to, by the resources in a given ecosystem. So all populations will, look at my mouse here, will initially increase like this on an exponential scale, but then eventually they'll reach a carrying capacity right up here, right, where they can be supported indefinitely. So no additional individuals can be supported, at least not for a long time. And when a population is maintained at its carrying capacity, the size of the population will generally be maintained in balance. So the number of individuals added will be in balance with the number of individuals that leave or that die. When one of the necessary resources is being used at a rate that exceeds the carrying capacity of the ecosystem, the population will eventually just be reduced in size until it's once again in balance with the available resource of its ecosystem. So as you can imagine, naturally in the wild or in everyday life, this carrying capacity is not just going to be a hard number that doesn't change. It's gonna kind of ebb and flow just a little bit. It'll get bigger every once in a while, maybe in like certain seasons, and get smaller in other seasons, but it will generally hang around a sustainable number. For the impact of limiting factors on exponential growth, we can see it. I have an example on the next slide with the population of northern fur seal. In the 1800s, the fur trade led to a drastic reduction in the population of the northern fur seal population, almost completely wiped it out. Its decline prompted the first international treaty ever, international, designed to conserve wildlife. It was signed in 1911. Let's take a look at what this did to the population of the seals. The graph below, or to my right, shows the growth and then eventual leveling out of the population of northern fur seals following the treaty. So right down here at the start, this is around 1911. This is how low we got that population to. There was only a couple thousand of them, or even less, just over 1,000 of them. And then signed the treaty, so they're no longer being hunted, and you can see that exponential growth returns. Now we have exponential growth because they're not being hunted for trade. But exponential growth is not sustainable. So naturally, the population reaches something we call the carrying capacity right up here. And this is the sustainable population size for that ecosystem that can last for a long time. So that's the carrying capacity. So right here, we have limiting factors that are affecting the population growth of the fur seals because it can't just continue to go up like this. And then it reaches a carrying capacity. Sometimes wildlife biologists and park or resource or like national park or resource managers need to know the carrying capacity of populations they're studying or managing. So sometimes they have to know how much of a population of a certain animal there is. They can do this by measuring the number of individuals in the population. They can do it either directly by actually literally counting them, or they can do it indirectly, more commonly by estimating. We'll finish on this next slide here. Populations of white-tailed deer are estimated through a method called pellet group counting. And yes, you might have guessed it, it's not a pretty job, but this involves counting the piles of pellets or feces that they have left behind during the winter months, all in the name of science. So yeah, might not be the most glamorous job, but there are people out there doing it. So I'm going to post that video on symbiosis for you. And a reminder that if you're watching this right now, today in just over an hour, I'll be posting a Google Meets meeting live for you to drop in and ask some extra questions if you have them. If not, we will see you after the weekend. Have a good weekend.